So in the previous lesson, learned about Reynolds transport theorem, about how a change of a extensive property, capital B, in my system changes with time based on how the related intensive property, little b, changes inside my control volume with time, and also how much little b comes in and out of my control surface. So last lesson we did this with little b equals 1, meaning big B was equal to mass, and found the conservation of mass relationship in integral form. Today what we're going to do is let little b equal velocity, which means that the big B, little b times mass, mass times velocity is momentum. And so what we're going to do today is derive the conservation momentum equation from Reynolds transport theorem. To do that, you want to remember from basic physics, Newton's second law, sum of forces is mass times acceleration, but mass and acceleration is derivative of mass times velocity, and mass times velocity is momentum, so change in momentum over time, that's going to go there. So what we get plugging all that in is sum of forces. So this is my change in momentum over change of time, which Newton's second law is sum of forces, equal to d by dt, integral over control volume of velocity with my little b, rho dv, integral over control surface, velocity, rho b dotted with dA. Now, unlike the previous example where we had, or the previous lesson, where conservation of mass was just one equation, this is a vector equation. So force, all three directions, has three components. So Cartesian coordinates can break that up into x, y, and z coordinate equations. So really this represents three equations. An x equation, force in the x direction, related to velocity in the x direction. So velocity in the x direction there. Notice this guy is not just velocity in the x direction. This guy refers to things coming in or out of that control surface. So he stays as a vector, b dotted with dA. So these two velocities are generally kind of different. That's why we keep them different. So x component, y component, again, velocity y, b dotted with dA stays as a vector. Same thing for z, vz, vz. The way we're going to use these equations is very similar to what we did for conservation of mass. Want to set up, first of all, your control volume, and then track everything coming in and out of your control volume through control surfaces. Want to set it up the same way. Hopefully try to make your control surfaces perpendicular to velocities. That way these integrals become easy. In terms of my forces, I then want to look at all the forces acting on my control volume. So the control volume part of this gets a bit more important when we do conservation momentum as opposed to what we did last lesson. So this process is best seen with some examples. So first example, have water flowing through this contracting drain. So coming in, inlet, have a pressure of 24 psi absolute. Drain diameter at that point is 6 inches. Comes down, gets contracted into a smaller diameter, 4-inch diameter pipe. Atmospheric pressure down here. Have some support holding this in place. Basically want to know what force is required by the support to hold that drain in place. So first step is to pick the control volume. So again, I want to have a control volume where I have a perpendicular to all inlets and outlets. So as long as I go straight across the top of this, where it's coming in, straight across up here, where it's coming out, that's all I really care about. Another thing I want to do though is label all my forces acting on this. So I have a couple forces. I have the support holding it up. That's going to provide some x force and some y force, possibly. So I have those two guys, Fx and Fy. I also have a pressure force pushing down on this surface, call it P1A1, so a constant pressure, that 24 psi absolute, pushing down on this inlet. Everywhere else is atmospheric, so everywhere else I'm just going to basically use gauge pressure and call it 0. Those are all my forces. That's my control volume. Next step is to apply conservation of momentum. So applying conservation of momentum, you're going to have two equations, an x equation and a y equation. So starting with the x equation, all my forces in the x direction acting on my control volume is d by dt integral vx rho dv plus control surface integral vx rho b dotted with dA. So I'm going to do this, take all my forces in the x direction. Based on my diagram, only have one force in the x direction, the force Fx from the support that I'm trying to find. So Fx, that force, is equal to, now inside this first integral, again I have a time derivative up front. So for this integral to not be 0, something inside this integral needs to be changing. Either the velocity needs to change, the density needs to change, or the control volume itself needs to change. It was said that the water is flowing steadily, so if it's flowing steadily, there is no time dependence for velocity, so that does not change in time. Water is incompressible, so that does not change in time. My control volume, I'm not making a change in time, so this whole first integral is 0. Then the second part of this, in my control surface, I have two places where it's coming in and out, so it's coming in at point 1, coming out at point 2. So the first one at point 1, I need the x velocity at point 1 for Vx, rho at that point, and then V dotted with dA, again, is not necessarily related to x, it's related to what's actually going in. So in this case, I have V1 in the y direction times A1, that's my V dotted with dA, and minus sign because it's going in. Then coming out, I have Vx2 coming out, that's my x component of that velocity, rho again, and then what's coming out of here is V dotted with dA, in this case V2A2, which is coming out, so positive in that case. And if I look at this, Vx1, my x velocity at point 1 is 0 because I only have y velocity, so no x velocity there, so that term is also 0. Then in terms of this guy here, Vx2, my velocity coming out, is technically in the negative x direction, so that guy actually becomes negative V2, and then rho V2A2, because all my velocity is in the x direction. So there's our force in the x direction. Similarly, want to do the same thing for the y direction, so all my force in the y direction is the time derivative of the control volume integral plus my control surface integral with Vy's in it instead of Vx's. So same deal, I want to take all my forces in the y direction. And in the y direction, I have a minus P1A1 pushing down, so minus because it's pushing down on that top surface. Also have Fy holding it up. Those are all my forces in the y direction. Then again, this time derivative integral, nothing in there is changing, so that goes to 0 again. And my control surface integral, again I have two surfaces, point 1 and point 2. So at point 1 I have velocity 1 in the y direction, rho, and then this guy, same as before, V1y A1 going in, so negative. And this guy over here, V2y, so what's coming out. And then again this guy's the same as before, V2x A2 coming out. So moving the P1A1 to the other side, I have this term, V1y is actually minus V1 because it's going down, so that V1y is negative V1, then this guy just becomes minus V1A1 times rho, and then this second one at point 2 down here, my velocity is only in the x direction, so V2y is 0, so that term's 0. So what I have for Fy is rho V1 squared A1 plus P1A1. So now that I have equations for Fx and Fy, my support forces, basically just need to plug numbers in, but I don't actually know the numbers because I don't know my velocities. I do know the flow rate though, so I can relate my velocities to flow rate, V1 Q over A1, so 4 Q over pi D1 squared. So my flow rate was 16 cubic feet per minute. So I want to change that into feet per second, so divide by 60 essentially. And then pi, my diameter, 6 inches, 0.5 feet, square that. Gives me 1.36 feet per second for V1 coming in the top. Similar to V2, same deal, other than I have a 4-inch, 0.33 feet diameter. So that gives me 3.06 feet per second coming out the bottom. So now that I have velocities, I can plug it in to find forces. So force in the x direction, minus rho V2 squared A2, so minus density of water, 1.94 slugs per cubic feet. Velocity V2 was 3.06 feet per second, square that. And then area 2, pi over 4, diameter squared, 0.33 feet squared, gives you a grand total of negative 1.58 pounds. So 1.58 pounds to the left essentially. So basically makes sense. If we have water coming down here, you can think of water being shot out of the bottom of this. That's going to want to push the other thing to the right. So basically momentum of the water pushing backwards on this thing is going to want to make it move to the right. My f of x needs to hold it, so it needs to push back to the left with that same force of 1.58 pounds. If that makes sense. So plugging in values for the y force, I have again 1.94. Now I have V1 1.36 feet per second squared, and area 1 half a foot for the diameter. But then I also have this pressure term, so 24 psi, that's absolute pressure. Notice when I did this, I only care about this pressure acting on this area. Everything else is atmospheric, so everything else cancels out. So because this is absolute pressure, and I've said gauge pressure being 0, I want to turn this into a gauge pressure, so take away 14.7 psi from that, turn it into a gauge pressure. Then I also want to turn it into the proper units, so psi, I want that turned into feet, so 144 square inches per square foot gets that into psf, which is what I want. And then again, this pressure of 24 psia is only acting on this area A1, so that's the only place it's not canceled out. So that area A1, pi over 4, 0.5 feet squared, gives me 0.7 pounds from the water contribution coming in, and then 263 pounds, the majority of it from this pressure force. So total 264 pounds in the y direction. Again, that's both of those are pushing this thing down, so my support's going to have to hold that up, so positive 264 upwards. Other thing that I kind of neglected in this was the weight of the water and the pipes. The pipe probably has some weight to it. The water inside there, whatever the volume of water is, I can figure out how much that weighs, and technically I probably should have added that onto this as well to hold it up in the y direction. So second example, I have a cart on wheels, total volume of 1.5 cubic meters, completely full of water, and then it has a water jet come in at a 30-degree angle into the top, and then the water shot out the back, straight out horizontally. And so I want to know what the acceleration of my cart is. Also want to know, at this instant shown, it's rolling over a scale. So what does the scale read? Assuming that the cart itself is weightless. So the cart itself has no weight, but there is the weight of the water inside it to take into consideration. So what's the acceleration, and what does the scale say? We're also assuming that the only way water comes in and out is through these two holes, so it can't come out the top or anything, so those are only two places water's coming in or out. So again, first step for any of these problems is to pick my control volume. So control volume, I'm going to go around my cart. Now notice over here, I have it coming straight up through this horizontal outlet, but then when I get to this 30-degree one, I basically shift it over so that it's perpendicular. So I have it coming off basically at a 60-degree angle through there. That's again going to make my integral easy. When I do v dotted with the a, it's just no cosines involved. You can do a straight box if you want, so just straight down through there. But then again, when you do that v dotted with the a integral, you need to work with some cosines of angles. It gets a bit more complicated geometrically. So easiest thing to do, that as I did, just angle your control volume so that it's nice and perpendicular. Then in terms of forces, I'm assuming atmospheric pressure is everywhere. So if atmospheric pressure is everywhere, solid gauge pressure all cancels out. Don't need to worry about it. Only forces I have in the y direction are the weight going down and normal force from the scale pushing up. No force in the x direction. I'm not worried about any sort of aerodynamic drag or anything. So no force in the x direction. So in the x direction, conservation of momentum, I have force in the x direction, d by dt, integral control volume, vx rho dd, plus integral over my control surface. Again here, I'm assuming everything's flowing steadily, so vx doesn't change, rho doesn't change, my control volume doesn't change, so that first integral goes to 0. Then in terms of my control surface, two things, one coming in, one going out. So again, I have some vi coming in, I want that in the x direction, and then rho v dotted with the a, again just negative because it's coming in, then v1 or vi ai, so whatever this area times velocity coming in is, it's just that. Then on the way out, I have v out in the x direction, rho, and then v out, a out. That's just in the x direction like we have. So putting that together, sum of forces, I don't actually have any force in the x direction, but I do have an acceleration, so I can replace my forces with a acceleration minus, because it's going to accelerate in the negative x direction, I'm assuming, and I'll be right. So I have a minus this v in the x direction is the x component of my velocity in. So negative, again, because it's coming in to the left. So this velocity is in the negative x direction, and I only want the x component of that, so cosine 30. And then rho minus v in a in, same as before. This guy is just rho v out squared a out. And now my mass, mass of my cart, because the cart itself is weightless, but there is water in there, so I need the mass of the water inside there. So density times volume of the water inside there, times acceleration. And then this guy becomes rho a in v in squared cosine 30 degrees plus rho v out squared a out. So continuing on, forgot to mention in the actual problem when I wrote it down that A1 and A0 are both 0.1 square meters, so the area of this inlet and outlet are both the same and both 0.1 square meters. Now to have the same area, from conservation of mass, water's coming in, has to go back out, so the amount of water coming in has to be the same as the amount of water going back out, meaning same areas gives me same velocities, so both velocities are 5 meters per second. So now that I have that, I can basically rho everywhere, can divide by rho, move the minus sign to the other side, so volume times acceleration is negative, these a's and b's are the same, so AV squared, pull that out, I have cosine 30 plus 1, then divide by volume, so my acceleration, negative area, velocity squared, cosine 30 plus 1 over volume, plug all those numbers in, 0.1 square meters for the area, 5 meters per second for my velocity, square that, cosine 30 plus 1 divided by the volume of 1.5 cubic meters gives an acceleration of 3.11 meters per second squared, minus sign just saying to the left, which I expected. So that was half the problem, finding the acceleration. The other half of the problem, we wanted to find what the normal force was, or what the scale read as this cart drove across it, which is the normal force. So for that, the conservation of momentum in the y direction. So y equation, sum of forces in the y direction, d by dt, control volume integral, y velocity, control surface integral, again with my y velocities. So in this case, all my forces that I have in my y direction, there's the weight, essentially the water inside the cart pulling down, and then this normal force from the scale pushing up, so that's what we're solving for. So normal force N, positive, upwards, minus weight, W, going down, so negative. Then again, I have this integral, nothing in here changes, so that integral goes to 0. In terms of my second integral, I have two components of it, one coming in. So coming in, I want the y component of that velocity coming in, rho, and then velocity times area coming in, with the minus sign indicating that it is coming in. That's for this stream at the 30-degree angle. Horizontal stream coming out, I have some velocity in the y direction coming out, density and velocity area out, v dot dA, positive outwards. So solving for my normal force, move the weight to the other side. I have v1y is y component, so minus coming downwards, sine of 30, so minus v sine 30 for that guy. And then rho of v and a coming in. And then this guy, v out in the y direction is 0, there's only x velocity there, so that guy is 0. So now my weight, rho vg. Then this guy, I have rho v squared a sine 30 degrees. So plugging all those numbers in, density water 1,000 kilograms per cubic meter, volume 1.5 cubic meters, g 9.81 meters per second squared, plus the second term, rho 1,000, velocity 5 meters per second, square that, area of 0.1 square meters, sine 30 gives 16,000 newtons, or 16 kilonewtons for the reading of the scale.